Yeah,
Yeah.
I'm good. Yeah.
Okay, maybe we'll make a start. Thank you everybody for coming. Of course, before we start, I'd like to acknowledge that we're meeting on the lands of the Ngunnawal and Ngambri people, the traditional custodians of the lands around Canberra. And I extend that acknowledgement to any Aboriginal and Torres Strait Islanders who are joining us from elsewhere here today. Today, ANZIC, the Australia-New Zealand International Scientific Drilling Consortium, we're really pleased to host Laura Wallace for a presentation. This is part of a new distinguished lecture series that we've resurrected, trying to bring some high-profile scientists involved in the scientific drilling endeavour from around the world to share their science and knowledge with the community around Australia and New Zealand. So I do have a couple of little slides just to introduce this whole thing. So, what is scientific drilling? At the moment, there's 2 international research collaborations in the oceans and the continents, which are dedicated to advancing scientific understanding of the Earth through drilling, coring and monitoring the subsurface. And those 2 programs are shown at the bottom there at the moment: the International Ocean Drilling Program, which Australia and New Zealand are a member of as part of ANZIC, and also the International Continental Scientific Drilling Program, which Australia joined last year and New Zealand has been a member of since 2009. And they take great pleasure in reminding us that we only just came on board last year. So why would we do this? Why would we drill into the subsurface? Of course, this is a tool for probing into the interconnected Earth system. So dynamic Earth, climate and environment, life, those processes, the health and the I can never say that word, habitability of the Earth, natural hazards, and all the cycles and rates of things that go on around the globe. So without those, the drilling into the subsurface, getting those samples, there'd be many things that we don't know about: hazards, earthquakes, tsunamis, the past climate variations that inform us about the future and that kind of thing. So ANZIC is a consortium of, I think it's around 18 universities and government agencies around Australia and New Zealand. So the ANU is a member. ANU hosts the office here, obviously. So everybody here is able to participate in the kind of things that ANZIC offers. And those kind of things are just summarized really briefly here. We support people being involved in these scientific drilling expeditions or projects. And there is a call just announced yesterday for an expedition in the North Sea. It's a paleoclimate expedition. If anyone's interested, come and have a chat to us. We sit down in Jaeger 4 if you haven't come down that way. But there's a range of other things we do. We offer some small grants, which are ideal for early career researchers. If you have some idea of a project that can somehow support this scientific drilling endeavour, then there's some, that's an annual call, which unfortunately closed a month or so ago. But we're trying to foster these global connections, travel funding for proposal workshops, various international workshops, conferences and booths, this distinguished lecturer series, which we've resurrected. And we're also about skills development as well. So we run an annual ANZIC Marine Geoscience Masterclass. 2 people from ANU are going to be going to Fiordland in New Zealand at the end of the year to take part in this year's masterclass. We've also helped support the Capstan at Sea postgraduate training initiative, which is done with CSIRO and University of Tasmania on the Investigator, and a bunch of other training courses around the world that we support people to go and participate in. But the offering that we're talking about today is the Distinguished Lecturer Series, and it gives me great pleasure to welcome and introduce Laura Wallace. She's our first esteemed lecturer in this new series. She's based currently at the GEOMAR in Kiel in Germany, and also has a professorship at the University of Kiel. Is also affiliated with the University of Texas at Austin, right? Yep. And at the time that she was doing a lot of this work we're going to hear about, she was based at GNS Science in New Zealand. And GNS actually doesn't exist anymore. You may not have caught that news, but in the middle of this year, GNS Science and NIWA, which is the Water and Atmospheres Agency in New Zealand, they merged to form a new entity called Earth Sciences New Zealand. Anyway, that's a little segue. But Laura is renowned as being the only female co-chief scientist from an IODP expedition from ANZIC, and in that 57-year history, that's a really great thing for ANZIC.
Just ANZIC,
Yeah. That's right. Yeah. And that's from participants. What is it, about 170 participants over the last 57 years, Sarah? 231. So from ANZIC since 1968. Yeah.
It's off the grass. Well, it's there.
So yeah, Laura is a global pioneer in slow slip event research. She's led IODP Expedition 375, which installed 2 borehole observatories off New Zealand on the Hikurangi margin. They were some of the first the first in the Southern Hemisphere. And her groundbreaking research is unlocking the secrets of fault mechanics, revolutionizing seismic hazard prediction with this cutting edge long-term monitoring that is only possible by drilling into the seafloor and deploying those kind of observatories. So I've talked more than enough. Yeah, maybe if you can welcome Laura and for her presentation. We really look forward to hearing what you've got to say, Laura. Thanks.
Getting relaxed and then you Okay, thank you for, I guess I'll change slides here. So thanks for inviting me to do this, and I really feel honored for you guys to have chosen me to kind of get your distinguished lecture series jump-started. And it's really, I appreciate the really amazing schedule Sarah's put together. I feel like I'm doing my grand tour of Australia these next 2 weeks. So, but anyways, I'm going to talk today about what I see as really some of the key results that we've gotten out of the Hikurangi subduction zone drilling. We had 2 IODP expeditions in late 2017 and 2018 to drill into the Hikurangi subduction zone. And before I jump into that, I want to acknowledge, as those of you who've been involved in scientific drilling endeavors, you know that it's not one person, involves lots and lots of people. And I just want to acknowledge some of these, and there's many more than that, but particularly the co-chiefs on expeditions 372 and 375. Phil Barnes and Ingo Pescher were co-chiefs on 372, and then my Damien Safer and I were co-chiefs together on 375, and those guys deserve a lot of credit for what's being discussed here. Also, the staff scientists, Katerina Patronotis and Leah LeVay from Texas A&M did a huge amount of work to help pull this off, particularly Katerina on the observatory side of things. She worked with us for 3 or 4 years in the lead up to the drilling to work on get the designs developed and get it all fabricated and everything. So she was really critical. And then a lot of others, particularly Stuart Henrys, Joshua Mountjoy, Dan Barker, did a lot of legwork on the site survey data and the safety case, and many other folks have been involved. So this is the work I'm going to talk about today. It involves some very extensive international collaboration between New Zealand, Japan, the US, Europe, and the UK, and particularly large chunks of funding from US NSF, partly through funding a lot of the IODP program at the time, and also the New Zealand Ministry for Business Innovation and Employment. And our international colleagues also got funding from quite a few other government agencies. All told, the work that's gone on at the Hikurangi subduction zone in the last decade is probably at this point involved close to 100 million New Zealand dollars. I guess that'd probably be 90 million Australian of international investment. There's been a really big effort by a lot of people. Okay, so just to jump into it, I don't know if everyone knows about slow slip events and slow motion earthquakes, so I'll give a little bit of an intro on that first, since we're very far from a plate boundary here in Australia. But what a slow slip event is it's very similar to an earthquake. An earthquake involves more rapid than normal movement along a fault, that slip taking place in a matter of seconds. So you get that sudden seismic energy release and shaking, where these slow slip events are very similar to earthquakes, except they take place over days to months, weeks, even sometimes years. And so you don't get that seismic radiation. You can have some tremor and earthquake swarms associated with them, but generally they're silent. And we've only been able to detect them in the last 20 years because of the advent of continuous GNSS networks at plate boundaries around the world. Particularly at subduction zones in the Circum-Pacific region. Slow slip events probably occur on every type of fault, but they're easiest to observe on subduction zones because you've got this big, broad fault that's dipping beneath the land. So you have a lot of surface area that you can have networks on top of to see these things happening. But they've really transformed our understanding of how faults work and have kind of generated a whole subfield of seismology and fault mechanics because of the questions that these things have raised. Before we really knew about slow slip events, we tended to think about fault slip in sort of two end members, either that stick slip seismic behavior or just steady creep. But now we know that there's this whole continuum of fault slip behaviors in between those two end members. And so there's been a very large number of questions that have been raised as to why this kind of slip behavior happens, and also how do these slow slip events relate to fast seismic slip events. We also know that these slow motion earthquakes, they're playing a very big role in accommodating the plate motion budget. For example, in New Zealand, the slow motion earthquakes at Hikurangi are probably accommodating about 50% of that overall moment budget. So they're a very important mode of the accommodation of plate motion at plate boundaries. And then we also know, for example, in the 2011 magnitude 9 earthquake offshore northern Japan, there's some really good evidence that that earthquake was actually preceded by a slow slip event that probably triggered that potentially triggered that magnitude 9 earthquake. And similar observations have also been made in Chile in the I think it was 2014 Iquique earthquake, and then another earthquake in Mexico, the Papanewa earthquake. So these slow slip events may actually presage a lot of large earthquakes. And so trying to understand that linkage between the slow motion earthquakes and the seismic slip, fast slip earthquakes, once we can understand that linkage, then maybe we can one day do a better job forecasting the large earthquakes. But we still have a long way to go for that. So the drilling that we did at Hikurangi and a lot of the other scientific work surrounding that was really targeted at trying to resolve a lot of the physical processes that produce these slow slip events. Okay, so just to get into the Hikurangi margin, the Hikurangi subduction zone here is offshore the east coast of the North Island of New Zealand. It emerges here at the Hikurangi Trough. And it's where the Pacific plate is subducting westward beneath the east coast of the North Island. And one of the big reason that this area was targeted for IODP drilling is because we have these really large, very, very shallow, slow slip events off the east coast of the northern Hikurangi margin, offshore the Gisborne area up here. This figure on the right is just a zoom in on that area. These black contours are the distribution of slip during a 2014 slow slip event that we captured with seafloor geodetic instruments. And we can also see these slow slip events happening with the onshore GNSS network as well. We see very large displacements during these, on the order of 3 or 4 centimeters of horizontal displacement over a few weeks. So initially it was the GNSS network that alerted us to the fact that these things were there, but then subsequent seafloor geodetic work really demonstrated how shallow they were and that they probably continue, if not all the way to the trench, at least to within a few kilometers of the trench. So the fact that they're happening so close to the seabed is really a globally unique opportunity to be able to actually, with scientific drilling, get our hands on the rocks that are involved in these slow slip events, and also measure the properties of these rocks, and also to undertake very near field monitoring, literally within a kilometer or two of the source of these events. So this was the motivation for going here. So we ended up, so again, this is off the northern Hikurangi margin, and this black line with these red dots are the transect that we drilled, and I'll talk a little bit more about that later. We drilled 4 sites for the slow slip problem in 2017 and 2018. And I also want to emphasize that I think one of the big benefits of a big scientific drilling project like this is it really kind of forms a centerpiece around which a lot of other work can also hang. Because you get so much insight from the drilling into the properties, it's really beneficial to also do seismic surveys. For example, here in 2018, there was a 3D seismic data set acquired along the drilling transect. That's a picture up here on the upper right that gives us a really high resolution view of the fault zone structure and plate boundary structure and properties. There was controlled source electromagnetic imaging along this transect here on the lower right, and it gives us a handle on the resistivity structure and the distribution of fluids in the plate boundary. So there's been some really exciting papers that have come out of that. We've been doing rolling seafloor geodetic experiments using seafloor pressure sensors. So with the seafloor pressure, these are continuously recording pressure on the seafloor. And if the seafloor goes up during a slow slip event, you record a pressure decrease. Or if it goes down, you record a pressure increase. And so that allows us to track vertical deformation of the seabed at a centimeter level. We've also been deploying ocean bottom seismometers, and so forth. So there's been a real large array of multidisciplinary experiments that have been done around this drilling. And so that's a big advantage of these big drilling projects, is it can really serve as a focal point for a lot of people to come together and bring their resources together to focus on a fundamental problem. And it's definitely something that, if you've got an exciting problem that you're really keen to get an international community to come together and tackle, this is a really great way to do it. Just to give you an outline of the talk, I'm going to overview the expeditions 372 and 375. Then I'm going to give you a few of what I guess the highlight reel of some of the key findings that we found from this, with regards particularly to the physical processes and properties controlling slow slip. Then I'm going to talk about some of the results that we've gotten from our observatories that we installed beneath the seafloor with the JOIDES resolution. And then finally, I'll talk a little bit about some insights that we didn't expect to gain about the seismogenic slip behavior further south at the Hikurangi subduction zone, away from the slow slip area. Okay, so this is just an overview of the IODP expedition. So this was done as 2 expeditions. And late 2017, we had expedition 372. And that, again, was Phil Barnes and Ingo Pecker were the co-chief scientists on that. And then in a few months later, in 2018, we had expedition 375. So 372 is really focused on acquiring logging while drilling data. So they basically drilled the holes and just measured logging data through the holes. Didn't acquire any cores on that expedition, other than from a small project that Ingo was leading to look at behavior of landslides in that area as well. But for the slow slip problem, we really just acquired logging while drilling data on 372. That was partly for safety reasons, because there was some concerns about potential fluid overpressure. There's a lot of gas hydrates in this area. They wanted us to collect logging data before we actually cored. And then 375 was really focused on acquiring the cores at the sites, and also installing 2 subsea floor observatories. These 2 expeditions were basically treated as one combined expedition. So we had collectively about 62 shipboard scientists between the 2 expeditions. You can see those photos at the top and the bottom of everyone who was involved. And it was about 13 and a half weeks of operations. And this involved a pretty large international investment on the order of 35 to 40 million New Zealand. So what were our objectives in the expedition? So we had 4 holes that we wanted to target. 2 of these sites were on the incoming plate, the subducting plate. So this is just a seismic line through this drilling transect here. And this is the deformation front here. And on to the right is the Pacific plate. So these 2 sites on the subducting Pacific plate were probably the 2 most important sites from the coring objectives, in terms of the coring objectives. And the purpose of these were actually to capture this part of the sedimentary sequence that's involved in slow slip. So you can see from the seismic imaging that the décollement, the plate boundaries forming in the lower part of the sedimentary sequence that's overlying this Hikurangi plateau, which is being subducted here. And so our major target was right here where that décollement is forming. And this would allow us to get our hands on these rocks that are involved in slow slip prior to subduction, sort of the protolith for the slow slip rocks, and understand the lithologies and the frictional properties and the fluid content coming into the system here. And we also drilled another site on top of the Taranganui Knoll seamount. We have a lot of seamounts coming in here. So those are also involved in the plate boundary in the slow slip area. And so that was to better characterize that. So that was number 1. And then number 2, we drilled a couple of sites on the overriding plate. So one right through a very active splay fault near the deformation front. And this is to sort of characterize an active fault in the system very early in its, or at very shallow levels. And then we also installed observatories at that site, and probably these two upper plate sites, then really the key purpose of those was for the observatories. And then likewise, we also logged, cored, and installed observatories back here at site 1519. Yeah, so the observatories were probably the biggest driver to go to these two. But it's also very important for understanding the upper plate stress regime, thermal regime, and properties as well. Okay, and we got really lucky. Doing this kind of stuff is challenging, and the stars aligned, and we were able to get everything done. And I think it was partly because IODP realized it was complex and challenging and gave us 2 expeditions to spread this work over. So it was we ended up having all of our objectives achieved. So going into the drilling expedition, this was kind of our main working hypothesis. Based on observations in other places and a lot of numerical modeling work, the community was converging towards the idea that a combination of factors could be playing a role in slow slip event occurrence. And these involved high fluid pressures were a major factor in this. Heterogeneity of the plate boundary is also another factor that people were thinking about, both lithological heterogeneity and also geometric heterogeneity. And then also transitional frictional behavior. A lot of the rock deformation experiments that had been done prior to this expedition on analogous types of rocks were suggesting that slow slip events may arise when you're in a transition from what we call velocity strengthening friction, which is frictional properties that support creep behavior. When you're transitioning from that to velocity weakening friction, which is frictional properties that support stick slip seismic behavior, that this may also enhance the likelihood of slow slip. And then temperature, understanding the temperature regime, which really heavily influences the mineral transformations and dehydration reactions and fluid release, is also very important to understand, and these low temperature metamorphic processes as well. So that was the hypothesis, the kind of main hypothesis going into this. So I'll talk about some of the key insights that we've gained into that from the drilling at Hikurangi. This is one of the first key papers that came out. This was led by Phil Barnes in 2020. And one of the big surprises that we really didn't expect prior to the drilling is that the intervals, so this is just a lithologic log from the site 1520 out here on the incoming plate. That was an incoming sediment sequence. And highlighted in blue are the intervals where the plate boundary is being formed right here. And so we found really quite a large mix of different types of lithologies in those intervals. Everything from mudstones to carbonates and marls, and then a very thick, and which we did not expect at all, very thick, very smectite-rich volcanoclastic layer, which we drilled for a couple of 100 meters. That was one of the bigger surprises, and I think that volcanoclastic unit, as you'll see in later slides, is actually a really critical aspect of the slow slip story here. So we have very heterogeneous lithologies in here. All of these will have quite different frictional properties. And then we also have a lot of geometric heterogeneity of the incoming plate, which you can really see from the bathymetry and also the seismic imaging as well. You've got these seamounts coming into the system. And there's been a lot of thinking that very heterogeneous stress distributions, which is what you would get in this sort of situation, would tend to promote a situation where you accommodate plate motion with slow transient events and a combination of smaller, moderate-sized earthquakes, which is what we see in this area. So the initial drilling results really supported the fact that heterogeneity at many scales plays a big role in the occurrence of shallow slow slip. One of the other there's been quite a lot of interesting work that's come out of rock deformation experiments on the core that was recovered, particularly from that input sequence interval where the fault zone is forming. And this is just some work both Hannah Rabinowitz and Srisharan Sridharan. They were both students that were on 375 and their work is showing that on the material that's where the décollement is forming, that you have a velocity dependence of your frictional properties. So when you're having imposing slow velocities, you have velocity weakening or stick slip type behavior. But when you ramp that up, that changes, that shifts to a velocity strengthening or more stable slipping behavior. And so that's a way to kind of keep the slip slow, because if you start to move too fast, it then strengthens and goes more to velocity strengthening. And so there appears to be a sort of slip rate dependence of these frictional properties of the rocks involved in slow slip. And then one of the other really kind of unexpected and exciting results as well was on these volcaniclastic materials, which I think is probably, these volcaniclastics are probably dominating the slow slip area based on what we retrieved from the drilling. And again, Srishar and Sridharan did some healing experiments on these and found that the healing rates of these rocks, so after they're exposed to a deformation event, then they heal over time. These rocks have extremely low healing rates. I think some of the lowest healing rates that have ever been measured. And so since they heal so slowly, even if you have very low tectonic loading, they're going to fail more frequently because they can't really recover their strength. So you're going to have very frequent low stress drop, slow slip events as a consequence of this really low frictional healing. So this was essentially kind of a new mechanism that was discovered really from these experiments on the volcaniclastic rocks at Hikurangi, a new mechanism that could help to explain the existence of slow slip events. One of the other really exciting results, and this is relating to the role of fluid pressure in slow slip event occurrence. People have thought for a long time that faults that experience these transient slow slip events may also have very high fluid pressures in them. So potentially even in some cases close to lithostatic, that would reduce the effect of normal stress on the fault and allow the fault to slip more easily and more frequently. And the volcaniclastic rocks, again, those volcaniclastic units that we were drilling in for days, what is very clear from those, they're very smectite rich and they've got a lot of water. So they're bringing a lot of water into the system, both that are bound in the smectite clays, but also in the pore spaces. And this was a really nice example of tying the drilling results together with the 3D seismic imaging. Up here on the upper right is just a VP model of the 3D seismic cube. You've got the slope here and the deformation front here, and you see this low velocity, this green area here coming in, and that low velocity persists some way past the deformation front. That low velocity layer is basically the volcaniclastics that we drilled. So you can see them carrying a lot of that low velocity is probably there because there's high water content. So Andrew Gaze and Damian Safer and some others were able to use the 3D seismic data and correlate that with what we were able to learn from the drill cores about the fluid content of that volcaniclastic layer. And they were able to sort of extend that insight to estimate the water volumes that were coming into the system here. So we basically had this really extensive, probably 2 kilometers thick. That volcaniclastic layer is probably about 2 kilometers thick on the plateau and is carrying a whole lot of fluid into the system. And this is just showing an estimate based on tying the drilling data together with the 3D seismic. This is the deformation front here, the subducting plates here. This is color-coded in terms of percent water content by volume. So these blue colors are sort of 40% or more water content. So that's what's coming in. And then that decreases, even, several kilometers past the deformation front, you start getting down to 25 or 30. So it's really bringing a lot of fluid into the system. So the shallow part of the plate boundary here is probably very highly overpressured. Okay, so and that really supports this idea that these slow slip event regions are characterized by high fluid pressures. Okay, so now I'm going to talk a bit about the IODP borehole observatories, some of the results from that. So I mentioned before the key aims at these 2 upper plate sites, it's 1518, U1518 and U1519, was to install downhole observatories to be able to monitor changes in the Earth's crust in the near field of these slow slip events. So site 1518, which is right out only maybe a few kilometers from the deformation front, penetrated a very active splay fault, the Papaku fault. And then site 1519 was we installed that in the Tuahini Basin, about halfway between the trench and the land. So the 1519 is about 40 kilometers offshore, and 1518 is about 85 kilometers offshore. So what we were actually monitoring here was a few different things. We had temperature strings. These are diagrams of our borehole observatories. We had temperature strings down the borehole, monitoring changes in temperature, which give us insight into fluid flow events and also the thermal regime. And we also had geochemical samplers in the fault zone here, the splay fault. This was actually, we went back to the observatories a couple of years ago to retrieve the temperature string and the chemical samplers and fluid flow meters. The temperature worked great. The geochemical samplers, fluid flow meters did not seat where they were supposed to seat in their titanium seat in the observatory and didn't collect any samples. So that part didn't work so well. But the part of the observing that I was most interested in that we did was we were also measuring pressure changes in the borehole. And so we did this we had hydraulic lines, basically stainless steel hydraulic lines running down the outside of the casing and terminating at different levels. So we had, for example, in this fault zone site, hydraulic lines terminating in the hanging wall within the fault zone and in the footwall. And we also had the same at U1519. And what these do is these hydraulic lines were connected to pressure sensors up at the wellhead. So they're conveying fluids up from the formation to the wellhead. So we're actually measuring the in situ changes in pressure in the formation. And the reason that we wanted to do this is it basically acts like a poor man's strain meter. I'm going to let that thing drop over. If you can imagine, if you have a slow slip event and you have squeezing of the rocks, you would have a pore pressure increase. Or if you're somewhere relative to the slow slip event where you undergo dilatation, you would have a pore pressure decrease. So we're basically wanting to track these slow slip events out, the crustal strain in response to these over many slow slip cycles. And this is just showing a picture of this is the wellhead at 1518. And this is one of our visits. That's a visit we did with our Canadian ROV ROPOS in 2021 to download the data. This is to download the pressure data. And basically to download that data, these are the pressure sensors over here in this bay over here that are getting the pressure conveyed up from the formation. And we've got data loggers there as well. And we have an underwater mateable connector here that we come in and we plug in with another underwater mateable connector with the ROV. And it's basically a serial connection that we can then communicate with the data logger and upload the data. So we've done that 3 times since they were installed. And I'll show some stuff from that. And Sarah and I were just talking about this morning, this observatory is called Te Matakite. And we actually ran a competition in New Zealand where students had to make a video and come up with a name for the observatory. And some students, I think they were in Hawke's Bay, won the competition. And they decided to name it Te Matakite, which means seeing into the future in Te Reo Māori. So that's down there. Their name is down there for many, many years to come. Okay, and so this is just what one of these observatory pressures records look like. So this is, in addition to having the borehole pressure measurements, we've also got a pressure sensor up at the wellhead. It's measuring the seafloor pressure. And this is what these records look like. So this bottom time series here is the seafloor pressure. And then the time series above that is pressure in the formation. And this is an example from Japan, but you can see the main difference between these two is that the borehole pressure is a little bit damped, and that's just a damping effect from the formation that's between the seafloor and the borehole sensing interval. But you can see the tides and all these other oceanographic changes are really identical between the two. So this reference pressure at the wellhead is how we can actually get rid of all the oceanographic effects, which is a big enemy of trying to do geodesy and crustal deformation on the seafloor. So this is a really effective way of of getting these very small pressure changes due to tectonic processes without being swamped by the oceanography. So this is that same record, I think, a shortened time period after the wellhead reference pressure has been removed. And we also estimate this tidal damping coefficient to remove that effect. But you're basically removing 99% of that oceanographic signal. So this is really giving us some incredibly high resolution records. This is just an example where an earthquake happened nearby, and you can see these are the seismic waves coming through, and you see a static change in the pressure, which may be related to crustal deformation due to that earthquake. So these pore pressure measurements, as I mentioned before, is really a proxy for volumetric strain. And how we can go from pore pressure to volumetric strain is because we've actually sampled the rocks, and we can measure the poroelastic properties of the rocks, the permeability, the compressibility, porosity, and then we can actually translate that through to volumetric strain changes. In the Hikurangi case, based on our work with the core samples, it's and also you can also use the tidal damping as to estimate this as well, but it's around 5 kilopascals per microstrain. Okay, so this is just showing some data from the first 2 years of observations of the Cork at the Cork observatories that we collected this in 2021 with ROPOS using the New Zealand research vessel Tangaroa. But this is a really interesting record. So I'll just show you the red time series on the bottom is actually the GNSS time series from a site right about here on shore. So the one that's closest to the observatory transect. So this is the east component of the displacement time series. And you can see normally that site's moving down, which is westward, but then occasionally you get these big eastward jumps, and that's the slow slip events. And so we had a big slow slip event in 2019 there that you could see at the onshore GNSS stations. And then in the observatory records, so this bottom black time series is the pore pressure record at 1519, which is the one closest to land. And then the top time series is from 1518, the one out near the deformation front. And you see this big pore pressure increase at 1519 that really tracks almost exactly with the eastward displacement history of that onshore GNSS station. And that's really suggesting that this site's seeing very similar things to what we're seeing with the onshore stations. But then when we go out to the 1518 site, you don't start to get this onset of contraction until about midway through the event, suggesting it's really starting later out there. And then you have this big pore pressure decrease, which is a dilatation. And you also see a mild dilatation at 1519 here, going on for probably a month and a half after we can see the event on the onshore GNSS station. So it's looking like number one, these events are lasting a lot longer than what we can tell with the onshore GNSS stations, which is giving us a lot of insight into the slow slip event process. And it also seems like it's probably migrating towards the trench. You have it persisting for much longer right out towards the trench. A rule of thumb to think about is that if your slip is down further down dip of your observatory, that's going to induce contraction. Whereas if the slip is further up dip of your observatory, that's going to induce dilatation. So these changes from contraction to dilatation are telling us something about the migration of the event along the plate boundary. And the fact that we've got dilatation at both of these sites in this later stage is suggesting perhaps there was slip right out at the deformation front. So this is probably our best evidence yet for slip right out to the deformation front, right out to the seabed. I'll just quickly show results of a slip model that I did for this event, breaking it into 3 stages. That early stage where we saw the onshore station and U1519 going, and then the second stage, and then the final stage. We also had some seafloor pressure sensors out during this event that showed uplift of the seabed during the event, and so we're including those as well. And if any of you guys do crustal deformation modeling or geodesy, one of the things that we're doing here is if those of you familiar with that field know 99.99% of crustal deformation models, people do assume that the Earth is basically a uniform elastic half space with 30 to 40 gigapascal rigidity. Out here, that just doesn't work. You've got this very low rigidity outer outer wedge and forearc juxtaposed against a very high rigidity slab. And you can't assume uniform half-space models. So we've used the seismic imaging to obtain the seismic imaging VP and VS, and then also estimates of density using other approaches to get shear moduli that are more realistic and representative. And so that's a key thing that you've got to do when you're dealing with particularly seafloor geodetic and especially the borehole observatory data, having that the constraints on the shear moduli and those borehole observing intervals, and we've actually taken that from the logging wall drilling, is critically important to interpret these data. So yeah, if you want to do seafloor geodesy at offshore subduction zones, you need to get some good seismic velocity models and preferably even insights from drilling as well. So this is just a slip model from the 3 phases. So I had phase 1 where most of the slip is sort of down dip and closer to land. And then we spread that out over much of the interface further up dip for phase 2. And then that phase 3 where those sites were in extension, we can fit that with just about a couple centimeters, 1 to 2 centimeters of slip on the very shallowest reaches of the plate boundary. So it's kind of amazing that we can detect slip changing and slip happening, you know, at that kind of 1 to 2 centimeter level. We wouldn't be able to do that with the kind of typical geodetic methods that we use onshore. So these borehole sensors are really, really sensitive. Okay. But I want to compare this with some of the other insights from the drilling. So this is just some estimates of fluid production. So if we think about how the fluid pressure on the plate boundary could be affecting the occurrence of slow slip. So Damien Safer took some of the incoming sediment. I think this was based on the volcaniclastic material, and looked at the fluid production at different levels going from the trench. This time the trench is on the left, and we're going deeper to on the right. So the blue are from compaction. So as that volcaniclastic sequence is being subducted and compacted, the red is from dehydration reactions of the spectite. And you can see this is overlaying, this is our total slip in the slow slip event. And we have these 2 peaks here. And that actually coincides quite well with these peaks in dehydration-driven fluid production. And where you have more of the dehydration-driven fluid production or compaction fluid production, you're going to have be more likely to have overpressure on the plate boundary. So this poses some tantalizing evidence that some of the details of how this fluid is being produced, as this big sponge is being subducted, may be influencing in detail some of the slow slip distribution. So that's an interesting result. And then one of the other more exciting things, we've seen lots of slow slip events in the borehole observatories. I don't have time to go through all of those, but this is, again, one of the more exciting observations here. And this is from some work being done by a student of mine and Damien's at the University of Texas, Mackenzie Carlson. And we had a sequence of large earthquakes to the north of New Zealand in 2021. There were 3 big earthquakes within, I think they were within about 12 hours of each other. It started with about a 7.3 just northeast of the North Island, and then we had a 7.4 and an 8.1 in the Kermadex within a few hours of that. There was a lot of tsunami warnings going on for most of that day after that. And the Kermadex event did cause a pretty decent tsunami in New Zealand. But what we saw in the boreholes right after that, immediately after that event, so this is top one is the Trenchward site, 1518. You can see the seismic waves from those earthquakes coming through. And you can see immediately after, particularly after the first event, we started to undergo a dilatation or a pressure decrease over a period of time, and then a very large pressure increase. And that pressure increase is actually the biggest transient deformation event we've seen in these borehole observatories to date, on the order of around a half a microstrain in terms of the deformation. And we didn't see anything at all onshore. There was no hint of any of this stuff going on with the onshore GNSS station. And then we saw dilatation through most of this period at 1519 at the one deeper down. So this is just some slip models that Mackenzie has done to try and interpret where the slip was going on. And again, this is in 3 stages. This yellow is stage 1, then this is stage 1 plus 2, and then that's 3. So 3 is really the cumulative slip. But it looks like the slip event, to fit the dilatation at both sites, we need slip right out near the trench. So it looks like the slip event initiated right at the toe of the plate boundary, right out here, and then propagated in the down dip direction. And we ended up with several centimeters of displacement at sort of 5-6 kilometers depth, sort of between the two observatory sites. And again, this was not seen on the onshore GPS. You know, that's a lot of motions, several centimeters. That's a couple years worth of plate motion. We're totally blind to this with our onshore networks. The only way we can tell these things are happening is to have these kinds of observatories out there to resolve what's happening out near the trench. And then what to also tie this back in with some of the other wider observations. If we bring this back to the work that Andrew Gaze has done to estimate the fluid volumes coming into the system, this is a cross section going from the trench here on the right down to about 15 kilometers from the trench. And this is, you know, showing about 45% fluid volume coming in and then decreasing. This area where that dynamically triggered slip initiated was really in this area of highest fluid volumes, an area of potential highest overpressure. And that's kind of where you would expect the triggering to be, because as these oscillating seismic waves come through and pulse through, the largest stress changes are going to be near the surface. But then if you have really high fluid pressure there, it's going to be more prone to slip. So that really makes a lot of sense that that's where that dynamically triggered slip initiated, was in this area of very high fluid pressure. Okay. And then I want to just make sure I'm okay on, I have a few minutes left. Is it about 10 to 11? Is that right? Yeah, okay. Got a few more slides. And then there's also been similar types of observatories installed offshore Southwest Japan at the Nankai Trough, and those have given us a lot of really interesting insights into shallow, slow slip events as well. And actually, IODP observatories in Southwest Japan enabled the discovery of the fact that they actually have shallow, slow slip events at Nankai, up dip of their seismogenic zone, of the area that ruptures in large earthquakes. And we see a lot of really interesting parallels between slow slip behavior in New Zealand and at Nankai. At Nankai, they also see this dynamic triggering from regional or distant earthquakes, and that seems to be focused near the trench. Those dynamically triggered slow slip events tend to be right at the upper end of the system, out near the trench. And they also see a lot of evidence for migration of these slow slip events. This on the left, this black time series on the left, I'm showing a couple of records from our more recent retrieval of data. And we see a lot of the spontaneous slow slip events, not the triggered, but the spontaneous, we see the signal first at the landward observatory, and then we see it later at the trenchward observatory, suggesting that those events are migrating right up towards the trench. And they see a similar thing in Nankai. So the spontaneous events seem to involve deeper initiation and trenchward migration. The dynamically triggered events seem to initiate right out at the trench. And in the Hikurangi case, actually propagate down dip. Snooze, sorry, my computer is trying to do an update. I don't want to do that right now. And then this here on the right, this is actually why I'm in the Southern Hemisphere right now. We just had a cruise on the New Zealand research vessel Tangaroa to retrieve a large array of seafloor instrumentation that we had deployed for the last 3 years in the area of these IODP observatories. So this is 1518 here and 1519 back here. And we deployed a large array of more than 50 seafloor instruments, a combination of seafloor pressure instruments, ocean bottom seismometers, and also oceanographic instruments. And these oceanographic instruments are measuring currents and changes in water column properties with an inverted echo sounder. And the purpose of those is to actually really map out the oceanography to even further reduce some of the influence of oceanographic signals on the seafloor pressure data. So we retrieved these instruments a couple of weeks ago, and we got about 95% data recovery, which has actually been our most successful cruise yet. So this is going to be really exciting data to interpret together with the borehole observatory data. And I think it's going to give us some really unprecedented insights. And this is actually probably the densest seafloor geodetic and probably largest seafloor geodetic experiment that's ever been done. Our stations are several kilometers apart. So it's going to be a pretty cool data set. And we actually had a very large slow slip event in late last year to the beginning of this year. That should say up to January 2025, located right beneath the network. So we should be able to see some really large signals on that data once we get a chance to dig into it. Okay, and then I'm going to finish up very quickly with some other insights that we've been able to gain about processes in another part of the Hikurangi subduction zone, and that's from really tying together some of the drilling results with some other seafloor geodetic measurements that we've been making. So this map here on the right. This is work based on work that we've been doing over many years using onshore geodetic measurements to try and constrain where the Hikurangi plate boundary is locked and building up stress for release in future earthquakes. And so what this is showing is it's a plan view of the subduction plate boundary fault. The red areas are the areas where the onshore geodetic data is suggesting the plate boundary is locked and accumulating a lot of elastic strain. The blue areas are the areas that suggest there's very little strain accumulation and the plate boundary is creeping aseismically. But a key aspect of this, you've got this strip of locking going right out to the trench. We have no idea if that exists, that we cannot resolve that with onshore data at all. And particularly up here, I think that really should all be blue. I mean, I made these locking models, but I don't believe a big chunk of it. And so anyway, so this whole area offshore is really unresolved. And so we deployed in late 2018, we deployed some arrays of acoustic transponders on the seafloor to use this technique called GNSS acoustic. So we deployed GNSS acoustic arrays, one out here offshore this very deeply locked patch beneath the southern part of the North Island, and then another one here, the central Hikurangi subduction zone in an area where we know there are slow slip events. This southern one's really the most important one and the one I'm going to focus on here because we did not know if the locking continued to the trench or if it terminates somewhere between the coast and the trench. And this is a really important thing to figure out from a tsunami hazard perspective, because if you are actually locked to the trench, you're going to be potentially more likely to have large slip to the trench in major subduction earthquakes, similar to what happened in Japan in 2011. So this is really important to figure out. And so the GNSS acoustic, we deploy these acoustic transponder arrays on the seafloor. And then we have what we call a wave glider here on the bottom left at the surface. And that wave glider is basically ranging to all three of the transponders in each array. Well, it does one array at a time. Basically, it sits right in the middle of the array. And the wave glider has two GNSS antennas on it, so we know the exact position of that wave glider. And we're able to then back out, after about 4 or 5 days of surveying, we're able to back out the position of the center of that array to within about a centimeter, within a known terrestrial reference frame. So like within ITR, the International Terrestrial Reference Frame. And then we can look at that in a plate fixed reference frame. So it gives us basically velocities that are very similar to what we could get with onshore GNSS. So this is what we, on the right, I don't want to focus in too much. I just want to show you the repeatability of the site positioning. So this is on the top is the north component of position for these two sites, and on the bottom is the east component. This is from each survey. And so we're getting a pretty linear looking change in that site position. And this is an ITRF 14. But the easier way to look at this and understand what's going on is to change your reference frame to Pacific plate fixed. So these blue vectors are the rate of motion of those sites relative to the subducting Pacific plate. So you can see you have very high rates of motion of these two stations relative to the subducting plate. This one in the south is moving at about almost 3 centimeters per year towards the Pacific plate, and you're only within several kilometers of the plate boundary. So this it's that shallow part of the plate boundary appears to be really creeping, and these red vectors are showing the predicted long-term motion at the trench based on what we know about the motion of the eastern North Island relative to Pacific. So we're actually moving at about 90% of plate motion rate at this site towards the subducting plate. So that's really suggesting creep at the trench, which is not what we see with the onshore stations. So this on the left, this now, I'll just confuse you even more and show you everything relative to Australia, although maybe you like looking at it all relative to Australia. But you can see this large scale clockwise rotation of the onshore GNSS velocity field. This is a long-term tectonic rotation. It's been going on for a few million years. It's seen in the paleomagnetic data and also the longer-term geologic deformation. And we see these red vectors are GNSS stations, and they're actually moving. The offshore ones are also moving very closely with that long-term rotation of the North Island. So on the right, I updated my, ooh. Ooh. It didn't like that. Oh, everything's space sorted. Okay. It doesn't like an Australian plate fixed reference frame here. Anyway. Okay, so on the right, I've updated my locking model using these offshore velocities and new offshore velocities. And I'm able to fit the onshore and the offshore data with pretty much creep starting at about 7 kilometers depth on the plate boundary off the east coast of the southern North Island. So we're able to fit both data types, both the onshore and the offshore data. Even though they're showing very different slip behavior on the plate boundary, we're able to fit those data with a transition to creep out here. Something I didn't mention before, any of you guys who know the geography of New Zealand, the capital of Wellington is right here. It's sitting right on top of this lock zone. So this is a really important issue for New Zealand in terms of seismic hazard. And the size of this lock zone, we potentially could produce on the order of a magnitude 8 earthquake on this. So it's a major concern for seismic hazard. Okay, so this result was actually extremely surprising. And if I was betting money, this is not what I would have bet on, that we would have seen creep out here. And that's because for a long time, in the absence of having this kind of seafloor geodetic data, people have postulated for many years that this area up dip of these lock zones should appear to be completely locked. And that's because we have this big locked patch here, and people assume that most of the loading of the shallower part of the plate boundary comes from creep down here. So you're basically insulating this near trench region from loading. So people have postulated that there should be what we call a stress shadow, where this is not necessarily frictionally locked near the trench, but it's kind of along for the ride with the locked patch below. You basically would appear to be locked. But this is completely the opposite of what we see here. And it's really suggesting that these stress shadows may actually be, that concept of the stress shadows may not actually be correct, that they might not be as widespread as people expected them to be. And I think part of the problem may be how people are thinking about loading the system. They're just thinking in a simple way of loading it with creep down here. In 2D, it's an even more extreme situation. But I think we really need to be thinking about it in more of a three-dimensional way. We have the eastern North Island rotating as a microplate doing its thing, and the Pacific plate subducting, and it's probably being loaded at all levels of the interface. And the creep or the slip behavior that we observe geodetically, I think may actually be more dependent on the local frictional properties than some of these other effects. So that actually highlights the fact that really the utility of seafloor geodesy to understand shallow megathrust behavior, because it may actually be directly revealing what the local frictional properties are. And that gives us a lot more insight into the future seismic hazard and future tsunami potential. The fact that this is creeping right now maybe make it less likely to slip and generate large tsunami would slip right out to the trench. So this could change the tsunami hazard picture here in New Zealand. The drilling does actually have a lot of implications for this because so we drilled that input sequence, and Phil Barnes at NIWA has done a lot of great work trying to use seismic lines collected along the margin to tie the input sequence from the southern part of the margin, which is this. This is an interpretation of Phil's of that seismic data. And Phil has found from tying the drilling with the seismic to the south that the plate boundary is really going to be hosted more in the sort of carbonate-rich material, these chalks and carbonate-rich marls that we drilled further north. And so we think the plate boundary down in that southern area is really largely composed of those carbonates, carbonate-rich material. And there's been some, again, Srisharan Sridharan and Damien Safer have done some really cool rock deformation experiments, and also some others have as well, on some of the Hikurangi material that was recovered from those intervals. And when you change the temperatures, when you're at low temperatures up here, you exhibit those materials behave in a more velocity strengthening sense. So they would tend to creep. Whereas when you go to greater than 100 to 150 degrees C, they shift into more velocity weakening or stick slip type behavior. And this is right around where we see this transition is right around that 100 degrees C isotherm based on some earlier thermal models that have been done. So we think that this transition from locking to creep is potentially determined by the thermal dependence of the carbonate frictional properties. So that the drilling has also played a big role in trying to understand processes on other parts of the subduction zone as well. So I'm going to conclude. But in terms of the slow slip problem, the drilling has really shown us that, heterogeneities of various scales and flavors are probably very important in enabling these slow slip events to occur, high fluid pressure, and also the frictional properties of the rocks that are involved. The healing characteristics are very important in promoting slow slip. The observatories are really giving us a whole new view into what's happening on the shallow plate boundary offshore the Hikurangi margin. We're seeing things that we had no idea were happening out there. For example, this dynamically triggered slow slip, which we cannot even see with the onshore GNSS stations. And we're also seeing much finer scale sort of migration and of these slow slip events on the plate boundary than we could ever see with onshore data. Something I forgot to mention is when you're looking at those pore pressure change time series and the onshore GNSS time series, the signal to noise ratio in the observatory data is much higher than with the onshore GNSS stations, which I think, again, really emphasizes the need to try and get more of these types of observatories out at other plate boundaries. And it's a real shame that the IODP program is a bit of flux at the moment, because the JOIDES resolution was a real workhorse for getting these kinds of observatories out there. And we need to figure out ways to do this in the current situation, because they are serving, they're really demonstrating the benefit of having this type of observing. And then at the southern Hikurangi margin, the seafloor geodesy is showing us a real surprise. We don't seem to have this stress shadow effect that people have postulated for a long time. And the drilling results are really suggesting that this change in coupling that we observe towards the trench is probably related to the temperature-dependent frictional properties of the carbonates there. So yeah, I'm happy to answer any questions. Thank you.
Thanks so much, Laura.
Okay.
I think you really demonstrated what the Hikurangi margin just across the sea over there is like the leading edge of understanding these subduction zones and their giant earthquakes. Yeah, so thanks so much for that.
Yeah.
Do we have questions?
Thanks for sharing this really incredible observation. And got two questions to start with. With the volcanic clastic materials, are they along the whole subduction zone? And then do you know, like, where do they even come from?
Yeah, that's a great question. And I'm glad you asked that, because I didn't have time to get into that. I'll go back to one of my earlier slides. So I think that, the nature of the Hikurangi plateau that's being subducted here, which one do I want? That one. So we've got the type of plate being subducted here. It's not normal oceanic crust. It's the Hikurangi plateau, which is a large igneous province that's a little more buoyant than normal oceanic crust, but it erupted sort of in a massive outpouring in I think in the late Cretaceous. And so when it was young in its development, you had a lot of seamounts sticking up above sea level, and those were eroded off. They basically were geo-type features. And so I think you spread a lot of that erosive material all over the Hikurangi plateau. So I think that volcanoclastic layer is probably widespread across the entire plateau. And it probably arises from erosion of those initial seamounts. So it's very important in this part of the margin, because much of the plate boundary is hosted in that volcanoclastic unit. But then when we get down into the south, where we have the locking, that steps up a level and is more hosted in some of the pelagic sediments and stuff, which, as we get to deeper levels, the carbonates, for example, would go to more of a velocity weakening stick slip type behavior. But there was a drilling proposal that was in a pre-proposal stage a few years ago. And I think the people got a little discouraged because of some of the uncertainties in the program. But to drill into this away from some of the seamounts where that volcaniclastic layer might be thinner, and can maybe even get further into the plateau and get a more comprehensive understanding also of the volcaniclastic layer. But did that answer your question?
Yes.
Yeah, okay.
And then so the second question is, what's the lifetime of once you install?
Yeah, I mean, it could be many decades. So these we did in 2018. The batteries on the data loggers should last for at least 10 years. And then we could actually go and we can actually pull the pressure package out and replace it with another one. So we could actually extend that for many decades to come. And what would be really nice, so in Japan, they've actually plugged the observatories into the DoNet network. So that data's coming in real time, and they can also sample at a higher rate because they're not having to worry about battery life. They can power it with the cables, the submarine cables. I would love, it would be a dream if I could get a cable up here, plug those things in, and we could be getting that data in real time. And I think seeing things like the dynamically triggered slow slip event, you know, we could see deformation events out there that potentially could lead into a large earthquake out there, which there have been magnitude 7 tsunami earthquakes hosted in that slow slip area. So I think there's a real important hazards case to actually get that data coming in real time for monitoring. So
I know that the New Zealand government is interested in actually bringing a submarine cable all the way to Channel Island, but then I'm not sure if they're still deciding which route to take.
yeah, we had a workshop a few years ago about that before I left GNS. They were thinking about from the mainland, somewhere in the North or South Island, to the Chathams out here. And that would have been perfect. And we were really pushing for them to do something off Gisborne and then come down. But I think that's sort of gone off the radar for now, because I think Starlink is providing quite a bit of connectivity for them at the moment. But we actually have a big project funded at GEOMAR that leading part of it, which is focused on developing smart sensing capability on telecommunications cables and installing nodes. And we have a lot of funding, and I'm kind of trying to convince everybody, let's just put it here, put it here, put a cable there, but we'll see what happens. So, yeah.
Other questions? Yeah.
Thank you. Very exciting talk, particularly for Australian seismologists, who are keen to learn more about seismicity. Yeah, so just actually looking at this paper, this figure, particularly the spot, the yellow spots. That's probably the located kind of a slow slip events. Is that my?
The yellow dots are tremor. So you probably are aware about non-volcanic tremor that occurs during slow slip events. So these are tremor events that have been identified from ocean bottom seismic deployments during sort of tremor occurring during 2014 slow slip events. Yeah.
So I guess related to that, is my interpretation right that thinking this kind of slow slip events is actually occurring almost like everywhere at the region where it's like creeping, right?
Yeah.
Or
when you look at the locking picture that I showed later, yeah. Yep. And I didn't have time to get into we basically have slow slip. I think this whole part of the margin and that entire part of the margin is failing almost exclusively in slow slip events. This red strip out here, I think that's not real. Yeah. So it's the slow slip events are I think accommodating almost all of the plate motion budget in that northern and central shallow margin.
I guess my final question. Related to that is obviously drilling is so expensive, right?
Yeah. So
what is the most effective tool actually to detect them?
Yeah, I mean, I think that you want to use a variety of approaches. Like, if you can get a couple of observatories in like we have here, but then complement that with seafloor pressure measurements, because the seafloor pressure has been really good at getting a sort of centimeter level vertical deformation. Having OBSs, I think, I mean, and from a monitoring perspective, I think you need in these systems really a cabled network like what they have in Japan with at least OBS and pressure on them. We've also been deploying, which is very promising, and we just recovered data. GEOMAR has, we deployed one right here of these things called direct path acoustic transponders, and they basically range to each other and measure changes in travel time. And you can, and then use that to look at baseline length changes between them. So we've got 2 of them deployed right just to the west of the trench on the ridge coming up from the deformation front, and then 2 of them on the incoming plate. So we'll be able to detect, you know, those slow slip events going to the trench. So we uploaded some data from those this year. I think multidisciplinary approach is always good, but I think that these types of observatories, if they can be installed, form a really effective core of something like that. And I think we can also figure out some cheaper ways of getting these things in, potentially maybe using seafloor drill rigs. You know, if we could potentially try and get them down to about 100 meters or so, I think that's still deep enough to get a good strain record. So, but I think that is an important challenge going forward in the IODP program, because I think these observatories are something very unique to the program that are really needed in a lot of places. So, yeah.
Yeah, I think around the year, like you said, that was the big thing, actually, I think I may for the first distinguished lecture for that, but specific reason that, but Australia especially needs to think more about rainfall temperatures versus
Yeah.
out of the strain community, and you don't have to up the cost, you just have to pitch the right science and.
Yeah.
We know that they're about to bring that 20, 40 million dollars.
Yeah.
Just
Thank you, go.
I'm just being aware of time because we have entered Laura has to have a lunch, right?
I'm gonna have to eat it.
One for the benefit of students maybe here. If you can just, thank you, by the way, for a very nice and pedagogical talk. And it would be nice for students to hear your perspective on the discovery of slow events itself. Can you clarify, was it seismology or was it geodesy?
It was geodesy. I think the seismologists hate that.
Did it work together? And, you know, just if you can give
Yeah, there was a little bit of serendipitous discoveries, both from the geodesy side and the seismology side. I think the key thing was in the Cascadia subduction margin off the northwest US and northern or southern Canada, southwestern Canada. GNSS networks were showing these transient deformation events, like the big chunks of the network were moving coherently. And the scientists there, the geodesists, realized, wait, we can fit this data with a deformation event on the subduction zone. And then at the same time, there was some interesting observations in Japan. Abara-san, a seismologist there, detected these tremor events, a non-volcanic tremor, and they then realized that these were happening at the same time as deformation events they were observing in borehole tilt meters in Japan. So there was this sort of convergence of observations, mostly from the geodesy side, but also from the seismology side. And this was all in, I think these papers were all published kind of 2001 to 2004. And so it was this big explosion of understanding, and it's really spawned a whole subfield. I mean, there are now dozens of seismologists and geodesists around the world who really focus most of their careers on studying these things. So it was a bit of a revolution at the time in terms of, yeah, thanks for letting me clarify that. And then we had one more.
Yeah, one more.
It's okay, we can go to lunch.
No, I'm hungry.
Okay. It was just again about the volcanic plastic layer, because from what you said to Boone, it sounded like that was quite unique to this location. Is that?
Well, I mean,
or,
I think.
Sorry, yeah, I was just wondering if that is the case, and if you think it is more pervasive or something similar to that or analogous to that exists at other locations.
Yeah, that's a really good question. The other locations of slow slip that I'm aware of, I'm not aware that they have these extensive volcanoclastic layers. I would expect you to find them where you are subducting these plateaus. You have this big outpouring, and also potentially things like the Louisville seamount chain, where that's coming into the Tonga Kermadex. You might expect that to have a lot of it. But I think there's other types of smectite, you know, you get a lot of smectite clays and sort of more, you know, like the Nankai Trough, you have a lot of smectite rich clays from the terrigenous stuff coming in. And so I think there's other sources for high amounts of smectite, but these volcanoclastics were particularly smectite rich, which we also didn't expect. But yeah, I think it's just really demonstrates the importance of trying to understand what's coming into the system as well. And yeah.
Right, thanks everyone. Look, I think you'll agree we've had a distinguished lecture from a distinguished lecturer. So thank you very much, Laura.
That's interesting. See this stuff going. With clients. I hope it wasn't too much with